coffee break. So after the lecture, there are some posters out, so we'll have a poster session, and the poster speakers will be standing in front of their posters and providing explanations. So I invite participants to come by and visit the posters. Thank you. John?
Okay, thank you. So we saw yesterday, I introduced the Ginsberg-Landau model and showed you how it wasn't invented to describe vortices, but it did describe them quite well. And that the structure of a vortex, the structure of the equations depended on this Ginsberg-Landau parameter kappa, and we had a look at what a vortex looks like in the limit that kappa was large, which is quite common for many materials. What I want to do today is to look at how vortices move about in the Ginsberg-Landau model. And we'll see a bit more today the analogy between superconducting vortices and fluid vortices. But if I'm going to tell you how things move, then I have to deal with time-dependent equations. And so far, yesterday, we only looked at steady-state equations for the Ginsberg-Landau functional. And Ginsberg and Landau didn't write down time-dependent equations. They came a little bit later by Schmidt, and then Gorkov and Eliashberg derived these equations from the microscopic BCS model of superconductivity. But they're more or less the simplest equations that you could write down that reduce to the Ginsberg-Landau equations in steady state. So they're a gradient flow of the Ginsberg-Landau energy functional. But because of this property of gauge invariance, there have to be a gauge invariant energy flow. And that means that instead of just putting a d psi by dt up here, you have a plus I psi times phi, where phi is this electric scalar potential. So E is the electric field, remember from yesterday. It's given by the time derivative of the magnetic vector potential, and then you get this gradient of phi, where phi is the scalar or electric potential. So this phi makes it up into this time derivative term here, so you have this sort of gauge invariant time derivative. So that's what you get for the variation of psi, and then you get, in here you get dA by dt in the curl squared A equation, and again you get a plus grad phi in there because of gauge invariance. And in fact, this equation is very easy to understand physically. So we saw that A is such that the curl of A is equal to the magnetic field. So the curl of A is the curl of the magnetic field, so that's the electric current. So this is the equation that's telling you what the electric current is. And what this equation now says is that this term over here we saw was the superconducting current. This is just telling you the total current is the superconducting current plus this extra bit. And this extra bit is just Ohm's law. So this term in brackets here is the electric field. So this is telling me the current is some constant times the electric field, and that's just Ohm's law. So this equation number 2 there is really just saying the total current is the superconducting current plus the normally conducting current. So I have some normal electrons moving about. They satisfy Ohm's law. And I have the superconducting electrons, and they give me this superconducting current. So just a reminder from yesterday that the potential A is only determined up to a gradient. Once you've given A, phi is determined up to a function of t. This constant sigma in here, I've described it as the conductivity of the material, the normal conductivity. Of course, I'm in dimensionless equations, so it's some measure of the conductivity relative to the other parameters in the problem. It's some non-dimensional number. In fact, I'm later going to take it to be 0 because it simplifies a lot of the algebra while you get the idea of the general case. So the difference between having sigma non-zero and sigma 0 is just algebra. There's no conceptual extra benefit. So this is the time-dependent Ginsberg-Landau equations, and now I have to add back in or remind you from yesterday what Maxwell's equations are, which are going to hold everywhere as well. So magnetic field is the curl of this potential A. So divergence of H is equal to 0. Divergence of the electric field is 0. I've got Faraday's law, which is dH by dt plus curl E is 0. And I've got curl H is equal to J. And so curl H would be zero, although I may have externally applied currents. So outside the superconductor, there may be a non-zero right-hand side here. You often consider the case where you don't worry about what it is that's producing your applied magnetic field. You sort of apply the field at infinity. So quite often you put this external current to be zero, and you just give a boundary condition that H goes to some known field as X goes to infinity. So these are the equations that I'm going to want to look at. And what I want to do is these are quite a complicated set of equations now. I want to see whether we can simplify them a lot by looking at vortex solutions to these equations, taking the limit in which this Ginsberg-Landau parameter kappa is large, so that I have this separation of scales between the vortex core and the variation of the magnetic field. And can I describe the solutions to these equations in a way which is much simpler? But before I carry on, I want to point out that there's a real coefficient of the d psi by dt here, which is different to the Gross-Pitaevsky equation that Eveline wrote down yesterday, which would have had an I in front of there. And so this is it's a dissipative set of equations, a dissipative system rather than conservative because of the lack of the I there. And we'll see how that affects the law of motion later on. Okay, boundary conditions. I've still got this. I'm going to keep the same natural boundary condition that we had last time. So this generalized gradient of psi is equal to 0 on the boundary. And along with that, I've got the usual boundary conditions on Maxwell's equations, which in the case I'm going to consider, where all the permittivity and permeability take the same value inside and outside, that just means everything is continuous. So the normal and tangential components of both H and E are continuous, and in addition, you can take A and phi to be continuous as well. In fact, most of the time, apart from in the particular simple case of a two-dimensional cylinder, usually I'm going to consider the superconductor to occupy the whole of space, so I don't have to worry about boundary conditions. But just for reference, that's what they would be if you really wanted to do the full problem. Okay, so I mentioned that this was a gauge invariant gradient flow. So the equations that you get still have this property of gauge invariance. And what that means is they're invariant under transformations of this type. So if A is only defined up to a gradient, so if I add a gradient function to A, then in order to make the equations invariant, I've got to take the time derivative of that function from phi, and all that does is change the phase of the order parameter. So this is the time-dependent analog of the gauge invariance we had yesterday, where I didn't have any electric potential yesterday. But exactly as we did with the steady equations, you can use this gauge invariance to write the equations in terms of real variables. So effectively, I can introduce this this gauge invariant potential. You can either think of this as a gauge invariant potential in that Q is invariant under this transformation, or if you like, you can just think of it as fixing the gauge. I'm going to choose this gradient function to be minus grad chi, and that fixes the gauge. But if you introduce this potential Q, so co Q is still equal to the magnetic field, what that means is that chi itself does not appear in the equation, so I've written the equations in terms of just real variables now. So this is the time-dependent version of the real Ginsberg-Landau equation we had yesterday. And you see the df by dt, because I didn't have an I in front of the d psi by dt term, the df by dt makes it into this equation, whereas in Gross-Pitaevsky, it makes it into this equation. So these are the real and imaginary parts of the complex Ginsberg-Landau equation for psi. And if I put an I in, the df by dt would have been in this equation, and that would have been d rho by dt plus rho u is equal to, div rho u is equal to 0. But in my case, it makes it into this equation, so this is some sort of nonlinear heat equation here. So that's the real and imaginary parts of the equation for psi. And then this is now the equation for the current, which takes, again, a nice simple form. This is the total current. This is the normally conducting current. It's just proportional to the electric field. and this is the supercurrent. In fact, so this is minus the current, this is minus the normal current, this is minus the supercurrent. So H is curl Q, and E is still minus dq by dt minus grad phi. So these are the equations that I'm going to use, I think, most of the time. They're a little bit simpler to look at than the complex versions. Okay, so one more thing before I start to do some analysis. We saw yesterday that the magnetic field associated with the vortex is quantized, and the units, or the magnitude of one quantum, was 2 pi over kappa. And I want to take the limit in which kappa is large, and I'm going to have lots of isolated vortices around. And so the magnetic field associated with such solutions is going to be 1 over kappa in size. And so I want to, in order that I don't get 0 at leading order and then I keep having to go further down the expansion, I'm going to recognize that I'm going to get a solution which is order 1 over kappa, so I'm going to rescale before I start. And so if I'm looking for vortex solutions, it's natural to use a slightly different scale for the equations, where you scale magnetic field with effectively the size of one quantum of flux. And once you decide to do that, you basically scale every variable associated with the field. So the potentials, the electric field, the electric current, and the scalar potentials all get scaled with 1 over kappa. So I'm going to make that rescaling, and then I'm going to drop the bars so that I'm just going to write the equations in terms of unbarred variables. But once I'm not going to go back to the original scaling, so from here onwards, it's these new scaled variables. And all that does is put the kappas in a little bit of a different place in the equation. So it was in front of the gradient term, but now I've scaled the potential. I can multiply up by kappa squared, and it just appears here. So I think there's a kappa squared here, and pretty soon I'm going to drop this term anyway, so we don't need to worry about that. So this is what it looks like in terms of psi and A, and then if you do the same thing with the real equations, this is what it looks like in terms of F and Q. So the kappa squared, which is going to be large, now only multiplies the F cubed minus F term. Okay, so I want to look again at the analysis that we did to look at the structure of a vortex at the end of the lecture yesterday. But I'm going to interpret it in a slightly different way. And we'll see, so we've seen for fluid vortices how when you take a vortex patch and you shrink the size of the patch, you can consider the idealized vortex solution where you have a delta function. So the vortex is the delta function in the vorticity. And I showed you yesterday that these Ginsberg-Landau vortices have this smooth but rapidly varying core structure, and you have this electric current, which is in the azimuthal or theta direction. So you see that the current is circulating, so you call it a vortex. But I want to show you today that the analogy is a bit stronger than that, that you can also consider superconducting vortices as delta functions in a certain equation. And that's what I want to derive just now. So I'm going to start by doing it in steady state, and then we'll move on, and I'll do the same thing for vortices which are moving. So in steady state, this is the same equations I had yesterday, apart from I've slightly rescaled with kappa, so the kappa is appearing in a slightly different position. And again, I'm going to expand everything in inverse powers of 1 over kappa, assuming that kappa is large. And so you can see immediately in this equation that if kappa is large, then F is going to be close to 1. And so away from the vortex core, the leading order solution here just satisfies F is identically 1. And when you put that into the second equation here, you now find that the potential Q satisfies curl Q plus Q is equal to 0. So these are the equations that are satisfied by the order parameter and the potential away from the vortex. So this just says that its background is at the maximum superconducting level. And for this equation, if I take the curl of it and just use the fact that H is equal to curl Q, then I can write this as curl H plus H is equal to 0. So if I didn't have a vortex, the solution would just be H is equal to 0, and everything would be superconducting. But the vortex generates a magnetic field, and so I'm going to get a non-zero solution to this equation because of the fact that the vortex is there. So this is true in general. I haven't restricted to 2 dimensions yet. So yesterday we looked at rectilinear vortices, and on the next slide I'm going to go to rectilinear vortices again, but this expansion so far doesn't require me to be in 2 dimensions, so this can be a full 3-dimensional vector magnetic field. But if you do specialize to the usual 2-dimensional case in which H is only in the Z direction, then you only need to take the first 2 components of the vector potential. And in fact, so this equation, curl H plus H is equal to 0. So curl is the same as grad div minus del squared. And if I have H only in the Z direction, and a function of x and y, then this H has got 0 divergence. In fact, that's true in general. So curl is just minus Laplacian. So the equation for the magnetic field away from the vortex is actually just minus Laplacian of H plus H is equal to 0. So what I need to know is which solution of this equation does the vortex correspond to? So if I didn't have a vortex, I'd just say H is equal to 0. The fact that I have a vortex means that I'm looking for a non-zero solution to this equation. And what we know is that as the vortexes approach, we saw from the asymptotic analysis yesterday that this potential Q, so remember Q is A minus grad chi, where chi is the phase of the order parameter, and near a vortex chi looks like theta, and so the gradient of theta is 1 over r in the azimuthal direction. So near a vortex, the vector potential Q is singular, like 1 over r in the azimuthal direction. And so this generates a singularity in the magnetic field of the vortex, which I can find, so I would take the curl, H is equal to the curl of Q. If I just go back and show you this equation here, so H is equal to curl of Q. So in fact, this equation here tells me that this is curl of H plus Q is equal to 0. Okay, so H is curl Q. So if I get rid of one of these curls, this is the curl of H plus Q is equal to 0. So Q is minus the curl of H. And so curl of H is equal to minus Q. If I use the fact that Q is 1 over r minus 1 over r e theta, then these two things together tell me that H must have a logarithmic singularity as the vortex is approached. And in fact, whereas the direction of Q is in the azimuthal direction, the direction of H is along the line of the vortex, as you would expect. So this is describing the fact that the vortex is a flux tube, that the magnetic field is directed along the line of the vortex. And so if H is only in the third direction, only in the Z direction, this just tells me that the magnetic field is blowing up like minus log of r as r tends to 0. So the solution I'm looking for this equation has got this asymptotic behavior as r tends to 0. So this equation is valid in the outer region, which means it's valid everywhere away from the origin. So I have this equation for r not equal to 0, and I have H looks like minus 1 over r as r tends to 0. And so I can write that in succinctly. Instead of writing this equation and this blow-up condition, I would generate that blow-up condition just by putting a delta function on the right-hand side of that equation. So the solution that I want to this equation is the one that corresponds to having a delta function singularity on the right-hand side. And because this coefficient is 1 here, that means I need 2 pi to be the magnitude of the strength of the delta function. So the vortex is looking like a delta function in the equation for the magnetic field away from the core. And the equation for the magnetic field is just this minus Laplacian of h plus h is equal to now 2 pi delta. And we've already seen what the solution to this equation is. When we did this asymptotic analysis yesterday, we saw that the solution was the modified Bessel function of order 0. And indeed, this has got this minus log r singularity, and the Laplacian of this guy is this delta function. So this is the equation in which vortices appear as delta functions. And it's exactly analogous to the corresponding equation in fluids. So let me show you what that one is. So this is sort of rehashing things you heard yesterday morning and this morning. So if I have a point vortex in 2 dimensions, so a rectilinear line vortex, in a fluid which is otherwise irrotational, incompressible, and inviscid, then the curl of U is the vorticity, is 2 pi gamma times the delta function. And divergence of U is 0 because the fluid is incompressible. And so here I've got a gamma, which is the strength of the vortex. So in 2 dimensions, so with a rectilinear vortex, I only have the first 2 components of the fluid velocity U. And because the divergence of U is equal to 0, that tells me there's a stream function such that the first component, U1, is equal to psi y, so d psi by dy, and the second component, U2, is minus d psi by dx. These so this is the perpendicular gradient, if you like. I take the gradient and then I rotate it by pi over 2. You can also think of it as taking the curl of the vector which is 0, 0, psi. So if you put the psi in the third component and then take the curl, this is what you'd get for the first 2 components of U. And this shows you that div U is equal to 0. U is the curl of something, so divergence of U is equal to 0. So the curl of U is the curl of this 0, 0 psi, which we've seen as just minus the Laplacian of psi. And so this first equation is just telling me minus the Laplacian of psi is equal to 2 pi gamma times the delta function. So this is the analogous equation for a fluid. So for a superconductor, I have minus Laplacian of h plus h is equal to delta function. For a fluid, I just have minus Laplacian of psi is equal to a delta function. So the analogy is between the magnetic field in a superconductor and the stream function in a fluid. So h corresponds to psi. And what that means is that the fluid velocity, which is given by the curl of the stream function, is analogous to the electric current, which is given by the curl of the magnetic field. So you have this correspondence between h and psi and between j and u. What are the points to notice about this correspondence between these equations? Well, I have this extra parameter in the fluid case. I have the vortex strength gamma. I'm free to choose this strength to be whatever I want. Vortices exist with arbitrary strength. In the superconducting case, that's not true. The superconductor has a quantized strength, and so I'm forced to have gamma as plus or minus 1 for a superconducting vortex. And then the final thing to comment on is that the equations are not exactly the same. So there's an analogy, but I don't. Here I've just got minus the Laplacian, whereas in the superconducting case, I've got this extra term. I get minus Laplacian plus h. And so what does that extra term do for you? Well, I mean, it doesn't seem on the face of it that there's very much difference between those 2 equations. But the key thing about this equation is that it's got so the first thing it does is it means that the decay of the magnetic field at large distances is logarithmic. So the current away from a superconductor, it decays like e to the minus r, because you get the balance between these two terms, balancing the second derivative of h with h, and even just looking at this solution, you know that this decays like e to the minus r at large distances. Whereas the stream function here just decays like 1 over r. The fluid velocity decays like 1 over r at large distances. So there's an algebraic decay of fluid velocity away from a vortex, whereas there's an exponential decay of magnetic field away from a superconducting vortex. And sort of even more importantly than that, exponential decay has a length scale associated with it. So there's a natural length scale in the superconducting equation. This length scale is 1, as I've written this equation, because I used it to non-dimensionalize. The length scale is the penetration depth. So whenever you have exponential decay, you have a length scale over which that decay happens. So this equation has a natural length scale buried in it, whereas the fluid equation doesn't have a length scale buried in it. So I write these equations down, and I don't know whether I'm talking about a vortex, which is the size of a hurricane, or a vortex in my teacup. I get the same equations in each case. So for fluids, there's no natural length scale. The same equations are valid at all lengths. Whereas for the superconductors, there is a natural length scale, and I've used it to non-dimensionalize the equation. So that, and that length scale is the penetration depth, the natural length scale for variation of magnetic field. And so we'll see a little bit later on how that turns out to be quite important. And I'll show you what the effect of having a sample which is much bigger than the penetration depth is later on. Okay, so I have the equation for the magnetic field, and the vortices are now appearing as delta functions in it. So everything is looking quite good. I've got this strong analogy with fluids, but for a fluid, I know what the law of motion is. I know that a fluid vortex just moves with the fluid. It's convected. So I work out what the fluid velocity is at the vortex, and I just convect it along. It's not clear what's the corresponding thing for a superconducting vortex. How should it move? So I can, given the position of the vortices, I can work out what the magnetic field is. Now what I need is the law of motion to update those positions, and then I can close the system. And that law of motion, I mean, everything is based on the Ginsberg-Landau equation. So that law of motion has to come somehow from the Ginsberg-Landau equations. So what do the Ginsberg-Landau equations imply for the motion of a vortex? So that's the calculation that I want to give you a flavor of now. And so this is the point at which the algebra is a bit easier, but it doesn't change very much if I just put the normal conductivity sigma to be equal to 0. So the equations just become a bit simpler. There's no time derivative in this equation for curl Q anymore. And it turns out that the scalar potential phi is just identically 0 in this case. Okay, so this is the set of equations that I've got is almost the same as the steady state equations. There's just a d by dt in the first equation, but everything else has got no d by dt's in it. And what I want to do is look at do this inner-outer expansion again, where I'm looking at the core structure of a single vortex and how it responds to the magnetic field in its vicinity. But I'm now going to allow for the fact that this vortex might not be stationary. So I'm going to assume that the vortex is at position x0, where x0 is possibly a function of time. And what I hope to find is what's the law of motion that tells me how x0 varies. So you know the procedure by now. I've got this large parameter kappa, so I'm going to expand everything in inverse powers of 1 over kappa. So I have my, I've only written it down for f, but I'm going to expand all variables in terms of f0 plus 1 over kappa f1, et cetera, et cetera. So I've just seen that away from the vortex, the the leading order outer solution, so outer meaning away from the vortex core, I just get from this equation F is equal to 1 identically. And we've just seen that you get this equation. This is known as the Landau equation for the magnetic field. So I get minus Laplacian of H plus H is equal to 2 pi delta, where the delta function is centered at the position of the vortex. And if I'm in an infinite domain, I might apply, well, I'd have zero field infinity. If I'm in a finite domain, then I'm going to have H tends to, H is equal to whatever the applied field is on the boundary of this domain. Okay, so that's what the leading order outer solution looks like. So now I need to say, well, what's happening in the vicinity of the vortex? So let me go and rescale near the vortex core and look to see what does the solution look like there. So we did this rescaling yesterday for a stationary vortex, and I just rescaled x. Little x is 1 over kappa times capital X to blow up the vortex core. And it's very similar here, apart from now the vortex is not at the origin anymore. So I'm blowing up in the vicinity of the position x0 where the vortex is. So I'm going to rescale and use capital X as my independent variable. And so when capital X is order 1, that means little x is within 1 over kappa of the position of the vortex. Okay, so I'm looking locally near the center of the vortex. And so that means any derivatives d by d little x is going to turn into kappa d by d big X. But the key thing about this being a function of time is that the time derivative by the chain rule is now going to have this extra term, which is, so d by dt ends up becoming d by dt in the new coordinates minus kappa times the velocity, which is x naught dot the gradient, where gradient means gradient with respect to capital X. Okay, so this is just by the chain rule when you change from using t and little x as your variables to t and capital X. So if I rewrite the Ginsberg-Landau equations in terms of these local variables, which have zoomed in on the vortex core, then this is what I get. I've used the subscript I just to highlight the fact that we're in the inner region now. So we're writing these as functions of capital X. And what's happened is that I get a kappa squared wherever I have a Laplacian. So I get a kappa wherever I have a spatial derivative. But I've divided by kappa squared. So originally there was a kappa squared here and 1 here. So I've divided by kappa squared. And here you see this combination of time derivative plus velocity dot gradient. So this is a bit like a convective derivative, if you like. You can think of this as d by dt minus u dot grad. Okay, so this is the set of equations that the inner solution is going to satisfy. And I need to solve these equations and match them with the solution that I've found away from the vortex core. So I know that the outer solution as I went inwards, Q was looking like minus 1 over r in the azimuthal direction. And then the next term will be some vector which will be constant when I evaluate it at the position of the vortex. So the asymptotic expansion of Q locally has got this singular term to start off with, and then the next term will be constant, and then there'll be some terms proportional to r, etc., etc. But we know that h looks like minus log r as r goes to 0, where r and theta are now local polar coordinates centered on the vortex, so centered on x0. So this form of the blow-up as q and h as r goes to 0 tells you how to start the expansions off in the inner region. So when r is small, q is getting large. So that means q in the inner region, in this inner region, r is order 1 over kappa. So that means if r is order 1 over kappa, then 1 over r is order kappa. So that means q is going to be order kappa in the inner region because of this blow-up. And likewise here, when R is 1 over kappa, H is going to be order log kappa in the inner region. And so the expansion that you need to postulate in the inner region, so F was bounded, so F is still going up in just inverse powers of 1 over kappa. Q is going up in inverse powers of 1 over kappa, but you've got to start it at kappa. So it goes kappa to the 1, kappa to the 0, kappa to the minus 1, etc. And then H is a bit funny because it's got this logarithmic term in the front because of the logarithmic blow-up of the outer solution as you go close. But in fact, I don't have to worry too much about H because I've written the equations just in terms of F and Q. So if I now postulate this expansion and substitute into the inner equations, well, you can see that I don't get anything apart from these are just the steady Ginsberg-Landau equations that we looked at yesterday. And the reason is that all these extra terms, the time derivatives, are all lower order. They've got 1 over kappa in front of them. So they don't appear at leading order in the inner region. So in order to match with the outer solution, F should go to 1, Q should go to minus 1 over R e theta as R goes to infinity. And so you find that because I've just got the same equations as I would have for a steady rectilinear vortex, and I've got the same matching conditions, you find that, in fact, these equations are satisfied by Q being identically equal to minus 1 over R e theta, and by F satisfying exactly the same equation that we got for a stationary vortex. So the same equations that we saw yesterday. And in fact, that's not surprising. What that says is that providing the vortex is not moving too fast, I've made some assumption on the value of x naught dot, but providing the vortex is not moving too quickly, the structure of the core is the same as the structure would be if it was stationary. So that the core might be perturbed a little bit, but it's not going to be perturbed a lot when it's moving. Okay? So the local structure of the vortex core, the way in which F goes down to 0, doesn't change when the vortex is moving. Okay, so that's all very good, but I still haven't got my law of motion. And in order to get a law of motion, I've got to get those time derivative terms to come in. And that means I've got to go to the next term in the equation. So I've got to write down here, this is just the leading order behavior. So this is the behavior of F0 and Q0. In order to get the time derivatives into the equation, I've got to go further down and look at the equation for F1 and Q1. And so that's where the further down expansions you go with nonlinear equations, the more terms you end up getting, the messier it looks. But this is the equation that you have to solve for F1, or the system of equations that you have to solve for F1 and Q1. And so these are the linearized versions, effectively, of that leading order equation for F0. But now it's not homogeneous anymore, because I picked up this v dot grad of the leading order solution here as well. So it's now a linear but inhomogeneous equation. And so this equation is a bit harder to solve, but in fact I don't need to solve it. I just need to know, does it have a solution? And in fact, the way it's going to work now is that I've got a boundary condition at infinity that says F1 should go to 0, and Q1 should go to this constant vector C. Remember, this is the constant in Q0 as I come in. So I had Q looks like minus 1 over R plus C. So this term jumped an order because of the 1 over R. When R is small, this became order kappa. This term is going to be matching with Q1 in the inner region. It's a smaller term than this in the inner region. So the boundary condition on this vector Q1 is that it should look like C at infinity in order that these two solutions match together nicely. And so I've got an inhomogeneous boundary condition and I've got an inhomogeneous equation. And this equation has non-trivial solutions with homogeneous data, because effectively it's the derivative of the equation that I got for, it's the linearization of the equation that I get for F0. And what that means is the derivative of F0 is going to satisfy this equation. if I just differentiate the equation for F0, I get the linearized equation for the derivative of F0. So effectively, by the Fredholm alternative, I've got an inhomogeneous system for which the homogeneous system's got non-trivial solutions. So there's going to be a solution to this system only if a certain orthogonality relationship is satisfied. And that orthogonality relationship is going to give me a relationship between this boundary condition C and this inhomogeneous term x naught dot grad F0. And that's going to be exactly the thing that I want, because that's relating the far-field behavior, or it's the behavior of Q in the vicinity of the vortex as far as the outer solution is concerned, to the velocity of the vortex. So that's going to give me my law of motion. So let me show you how, one or two steps in how you derive that equation. So the first thing is I'm going to simplify this a little bit now, that because I have the curl of Q1 is equal to 0, I can write Q1 in the inner region as the gradient of a potential. And then if I want this boundary condition to hold as r goes to infinity, then this potential, if Q is going to a constant, then phi has got to be linear in x at infinity. And so phi is going to be c dot x. And if I write that in terms of polar coordinates, so if c is c1, c2, or rather the modulus of this is c and the direction is from the x-axis is alpha, if I write c in this form, then that tells me phi must be in this form. So that's just a little bit of elementary trigonometry. But this boundary condition is going to tell me what sort of solution to look for of these equations. So I know that phi has got to look like this, and what this tells me is that the right form of solution is, effectively I can pick out what the theta dependence of solutions is. So I know that F should have a theta dependence, which is sine of theta minus alpha. We've just seen phi has got this cos of theta minus alpha in order to satisfy the boundary condition. And the velocity I'm going to pick to be in, well, given that I know what the answer is, I'm going to choose the velocity to be in the right direction and show you that it works. And then we'll interpret what direction that velocity is later. So this is the direction of the velocity. It's in the minus sine alpha cos alpha direction. And the modulus is equal to u. And then, so this is in Cartesian, so I've got to write that in polar coordinates. So you get one component in the r direction and one component in the theta direction. So if you look for a solution to the equations of this form, because the leading order solution was only a function of radius, r, and the first order equations end up being linearized, so the coefficients are only functions of r, and so you find that you can satisfy the equations with functions of this form, with effectively a Fourier mode, sine theta and cos theta. So you find that when you substitute it in, you end up with ordinary differential equations for these coefficients eta, nu, and phi. Just eta and nu. So this is the pair of equations that you now have to solve, where this F0 is this solution of the leading order problem. And so you could now stick them on the computer, but you can also now look at these and derive the solvability condition. And the way you do that is you multiply the leading order, you multiply this equation for, effectively the equation for F1, you multiply it by r times the derivative of F0, and you differentiate the equation for F0 and multiply it by F1, which is r times eta. And then you subtract the two and you do a bit of simplification, and you find that you get an exact derivative term from all this mess here. But you're not quite there. So if I just had a single equation, that would be the recipe and you'd be done. You're not quite there because you've got a system here, so you've still got a bit of other stuff to do. But you can use this second equation to eliminate this term. And again, after a bit more simplifying, then you end up with this single equation, which is the whole of the left-hand side now is an exact derivative. Okay, so that's just the same equation written again. So so is there a solution to that equation? So the right-hand side is some known function. Okay, the left-hand side is an exact derivative. The right-hand side is the leading order solution to the leading order problem. So I can integrate this now from 0 to infinity. And if I apply the boundary conditions, then this tells me, so this left-hand side, this guy tends to 0, both at the origin and at infinity. This guy tends to 0 at the origin, but it doesn't quite tend to 0 at infinity because this nu is growing linearly at infinity. And so what you end up with is this limiting behavior of nu prime plus nu over r is equal to the integral of this guy here from 0 to infinity. But then since I know what the linear behavior of this at infinity is, this guy is just proportional to c, and this guy is proportional to u, and so you end up with a relationship that you can solve this first-order system of the system for the first-order solution for f1 and q1, providing u is equal to some coefficient times c, and this beta here you can work out what it is in terms of the integrals of the leading order solution. So that's just so. Mathematicians think of this as the Fredholm alternative. Physicists think of it as integration by parts. In any case, it's the solvability condition that if this relationship is not satisfied, you can't solve that first-order equation, the system of equations for F1. And so this is what gives you the law of motion between the behavior of Q at infinity and the velocity of the vortex. So what have we found? I've found that u is proportional to c, but now I've got to go back a little bit and look to see which direction it was in, because I showed it to you, but I didn't sort of interpret it for you. So remember that q, the behavior of the outer solution, so this is a way of linking what does q look like away from the vortex to what the motion of that vortex is. So as I come in, the outer solution had this 1 over r singularity, and then c was the next term in that expansion. And I said, well, suppose c is in this direction, cos alpha, sine alpha, so that the angle that c makes with the x-axis is alpha. And the ansatz that I made for the velocity was in the minus sine alpha, cos alpha direction. So this velocity is rotated with respect to c by an angle of pi over 2. Okay, so this velocity is orthogonal to the vector c. So the law of motion is that the velocity is proportional in magnitude to c, but the direction is rotated by pi over 2. But now I've still got to interpret what does c mean for you as well. So c, the velocity is the regular part of q as you approach the vortex. But now let me go back and look at the outer equations. So we found that we had curl q plus q is equal to 0, or minus curl squared q is equal to q. And then the curl of q is just h. So in this case, that's naught h. So this is telling me, again, that so q is equal to minus curl q, which is minus curl of h. And so q is just minus the perpendicular gradient of h. So the curl of 0, 0, h is just minus hy, comma hx, comma 0. So now what I have to do is rotate this by pi over 2. So this is sort of the perpendicular gradient. So if I rotate it again, what I end up with is minus the gradient. So q perp, q rotated by pi over 2, ends up just being minus hx minus hy. So I get minus grad h. So the direction of the velocity of the vortex is in minus the grad h, where, well, I've got to take off the 1 over r term. And so it's the regular part of the gradient of h evaluated at the vortex. So the vortex velocity is proportional to the regular part of minus grad h there. And through this analysis, you know, in fact, what the constant of proportionality is. It's some integral of the leading order solution that you can calculate numerically. So this is what the summary is for a single vortex. So the outer problem satisfies minus Laplacian of h plus h is equal to 2 pi times a delta function centered at x0. That's inside the superconducting domain. If I have a finite superconducting domain, I might apply h is equal to some boundary value on the boundary. And then how is this point going to move? Well, what I do is look at the solution to this equation. I take its minus the gradient, and then I evaluate the regular part of this at the position x0, and that tells me what the velocity is. And so I've tied it up a little bit. There should have been a beta in front of here, which is the coefficient we just worked so hard to derive. But of course, the only place time appears in this problem is in this x dot, so I can rescale time to make beta is equal to 1. It's just a rescaling of time. So this is the simplification of the Ginsberg-Landau equations for a solution in which there's just one vortex and it's rectilinear in the z direction. So this system is considerably simpler than the time-dependent Ginsberg-Landau equation, so we've made quite a lot of progress in deriving this. It was implicit through what I did there that I had the local behavior of Q was always minus 1 over r e theta. So implicitly, I was taking a plus vortex. So I was taking a winding number of plus 1. So if you do it again and you say, well, what happens if you change the winding number? Well, so two things happen. One is that the strength of the delta function, I said, could either be plus or minus 1, depending on whether you had a plus vortex or a minus vortex. So this n would appear in front of this delta function as either plus or minus 1. And then the second thing that happens is that only plus vortices go down the gradient of magnetic field. If you had a minus vortex, it goes up the gradient of the magnetic field. And so you find that the law of motion also gets switched. So you have to put an n in front of here as well, so that this n is plus or minus 1, depending on the sign of the vortex. Okay, so that was all for one vortex. But the nice thing about the equation we've ended up with is that it's linear. And so that means if I have two vortices, then if I want to work out what magnetic field they generate, I just have to put two delta functions on the right-hand side, because I can take the field from one vortex and I can take the field from the other vortex and I can add them together. So if I have a system of vortices, all I do is have a sum of delta functions on the right-hand side, where each one can have a different strength, but all the ni's have got to be either plus or minus 1 because the vortices are quantized. And again, I would apply a magnetic field on the boundary, and now the ith vortex moves in the direction of the gradient of the magnetic field, the total field generated by all the vortices, and the direction that it moves depends on its own winding number. So the field strength depends on all the winding numbers of the vortices, but the direction that a particular vortex moves depends on its own winding number. So that's in contrast again to fluids, where a fluid vortex spinning one way or a fluid vortex spinning the other way, they all get convected with the fluid. It's not that some go with the fluid and some go against it. So the law of motion for a fluid vortex is always that it's convected with the fluid. Whereas for a superconducting vortex, it depends on whether it's a plus or minus to which way it goes. So let's look at some simple situations in which we can interpret this law of motion. So this is a plot of the magnetic field due to one vortex, which is that at the origin there. So I imagine I have two vortices. So if I want to work out how the second one moves, then it doesn't move due to its own field, because that's just generating a singular part in an infinite domain, so no boundary effects. So if I want to work out how the second vortex moves, I just have to look, well, what's the magnetic field that the other guy is generating? So this is the magnetic field that the other guy is generating. So if I put a vortex down somewhere, it's going to move down the gradient of that field. It's going to move in the minus grad h direction. So if I put a vortex here, it's going to move in that direction. If I put it here, it's going to move in that direction. So it's going to be repelled from the first vortex. Okay? And the strength of the interaction is strong. It's going like the gradient of the field. So that's going like 1 over r as r tends to 0. So the strength is very strong locally, but it decays exponentially as you go away. So this is the motion of a positive vortex due to another positive vortex. So like vortices repel each other. The interactions are along the line of centers, and they repel. So this is, I've put now a negative vortex down. So the field is negative, and I'm looking to see what's a positive vortex going to do. So positive vortex means it moves down gradients of the magnetic field. So this time, the gradient of the magnetic field is directed towards the origin. And so if I have a negative vortex here, and I put a positive vortex here, it's going to be attracted to it. Okay, so a negative vortex is attracted to a positive vortex, and vice versa. So here, a positive one is attracted to a negative. So it's like charges. Opposites attract, and like vortices repel each other. So what about vortex boundary interactions? So suppose I have a vortex here. Suppose this is the superconductor on this side, and this is just free space on this side. So I put a vortex down here. It's a solution of this Landau equation, minus Laplacian of h plus h is equal to 0. And suppose I don't have a magnetic field on the boundary, so I've got 0 magnetic field imposed on this interface. Well, so the single vortex solution doesn't satisfy 0 magnetic field on the boundary. It's some modified Bessel function. So in order to have 0 field on the boundary, I have to introduce an image vortex. And the image vortex is going to be equal and opposite. If I have a plus 1 here and a minus 1 here, then I'm going to have 0 field on the boundary. Okay, because whatever I get from the plus is going to cancel with the minus. So that says when you put a vortex next to a boundary with 0 magnetic field, you get an image vortex which is equal and opposite. And we've seen that opposites attract. So that tells you that vortices are attracted to boundaries. Okay. Effectively, it's attracted to its image in the boundary. It's So there's a magnetic field due to the vortex, but there's no applied field on the boundary. So I'm just saying the only field generated here is due to this vortex here. And so the solution in this, on the superconducting side, would be a Bessel function centered here and a Bessel function centered here, but evaluated on this side. And then the solution on this side of the boundary would be 0. There'd be no magnetic field outside. But to get the solution inside, I have to imagine there's an image vortex outside. It's this simple way of seeing what the solution to the equations is. It's similar to sources and sinks, exactly. Okay, so that's without a magnetic field on the boundary. But what if I do have a magnetic field on the boundary? So if I have a value of h on the boundary, suppose I just have a half space and I give h is equal to h naught on the boundary, then I'm trying to now find what's the solution of the equation, the London equation, which is minus Laplacian of h plus h is equal to a delta function with h is equal to h0 on the boundary. But because it's a linear equation, I can just add the bits up. So I've got the solution due to the vortex itself, the free space solution, which is k0. If I give its image, then that would get me h is 0 on the boundary. So to that, I've just got to add what's the solution, the vortex-free solution, which has h is equal to h naught on the boundary. And that's just a one-dimensional solution. So I'm solving hxx is equal to h. So that's just a hyperbolic cosh. So there's the boundary field, the field in the interior that you get due to the boundary value h naught is just a cosh of x. And so now the gradient of this guy is it's pushing this positive vortex in that direction. It's going down the gradient. So this boundary field is pushing the vortex into the superconductor, but its image is pulling it out. So you have a competition between these two effects. The boundary field wants it to go further in. The image wants it to come further out. And in fact, this competition is sort of not equal. So the boundary field is just h naught cosh of x. So as x goes to 0, the gradient of that guy just goes to h naught. It's bounded. But the image, as the image gets close, we've seen that the gradient of the field looks like 1 over r. So when the vortex gets close to the boundary, the image always wins. Because the image, the strength of the attraction to the image goes to infinity, whereas the strength of the boundary field is just finite. So whenever the vortex is close to the boundary, the image wins and it gets sucked out. Whenever it's a long way from the boundary field is decaying like h naught e to the minus x. But the image field is decaying like e to the minus 2x. Because if the vortex is at position x, its image is at position minus x. So the distance between the vortex and its image is 2x. And so the image field decays like e to the minus 2x. The boundary field decays like e to the minus x. And that means that the boundary field always wins at large distances, okay, because the decay is slower. So what that says is that there's always some point in between where these two things exactly balance with each other. And if I'm on this side, then the vortex is going to get sucked out. And if I'm on this side, then the vortex is going to get pushed further in. So there's always this region near somewhere near the boundary where if a vortex wanders there, then it's going to get sucked out. And so that's what you would get for a half space. And you get something similar if you have a finite superconductor, providing it's big enough that the boundary doesn't always win. You will find that there's, depending on the strength of the applied field, there'll be some curve, which is the domain of attraction of the stable point inside the superconductor. And if you start off with a vortex inside this curve, it'll get sucked inwards. But if you start off with it outside this curve, it'll get sucked towards the boundary. Okay, comparison with fluid vortices. So, as I've said, a vortex in a fluid just gets convected with the fluid. So the law of motion is just that v, the velocity of the vortex, is equal to u, the velocity of the fluid. So a superconducting vortex still has a velocity which is proportional to the current, but it's not in the direction of the current, it's in the perpendicular direction. So for fluid vortices, we saw that there was this stream function that u is equal to curl of psi, which is psi y minus psi x0, which is this perpendicular gradient. And so the equations, just to remind you what you saw this morning for a fluid vortex, are that minus Laplacian of psi is equal to the sum of delta functions. The psi is 0, for example, on the boundary, but the law of motion is not that it's minus the gradient of psi, it's the perpendicular gradient. And so it's still proportional to the gradient, but it's in a different direction. And so that means that if I have two like fluid vortices, we saw from Eveline this morning that they will rotate around each other. So this vortex spinning in this direction generates a fluid velocity which is down. This vortex spinning in the same direction generates a fluid velocity over here which is up. And so together they'll just spin, if they're equal strength, they'll spin around the center of mass. So the two vortices will spin around a point directly in between them. Whereas for a superconductor, if I have two like vortices, then the motion is orthogonal to that and they'll separate. And similarly, if I have unlike vortices, if this vortex is spinning this way in a fluid, it's generating a velocity here which is down. If this one is spinning this way, it's generating a velocity here which is down. So the two vortices, if the strengths are equal and opposite, will just move off in the downward direction, maintaining their separation, whereas for a superconductor, the opposite vortices will end up attracting each other. I'm not going to say anything about that. So the last thing I want to talk about today is homogenization, which is sort of the opposite. Well, it's exactly related to what Evelyn talked about this morning. But whereas for a fluid, you can sort of start with a vorticity and say, let me imagine that vorticity as a lot of point vortices. How are they going to evolve? For a superconductor, I don't have any equation for how the vorticity should evolve, because I never started off with vorticity. What I've started off with is point vortices. So in some senses, for a fluid, the point vortices are an approximation to a continuous vorticity that are convenient. Whereas in a superconductor, it's sort of the other way around. What we really have is point vortices, and what we would like to have is a vorticity. So how can you write down something which is equivalent to the Euler Equations, given that you're starting off with point vortices? So I'm going to do this in a very hand-wavy, sort of applied, non-rigorous manner. But you can do all this with weak solutions and test functions and things. The way I like to think about it is a sort of homogenization process. And one way to interpret it is just to define, so I'm going to define a vorticity by, so what's the vorticity at a point? So I choose a point, and then I choose a circle centered on that point. And I'm going to integrate my sum of delta functions over that circle. And that's just going to count how many vortices are there inside there. So effectively, the test function I'm using is not very smooth. It's 1 inside the circle and 0 outside. But you sort of, bear with me. And then, that's the integration I'm going to do. So I'm going to count how many vortices there are inside that circle, and then I'm going to normalize by the area of the circle. And then I'm going to consider a limiting process in which the separation between vortices gets small, so that they're getting closer and closer together, but also this circle is getting small in such a way that there are lots of vortices inside there. And so I'm going to find that, so the circle tends to a point, but it still contains lots of vortices. And so that's the limiting process that I want to do. And so that for this omega, so for fluid vortices, it was very important that you were allowed to let the vortices get weaker and weaker. So as you put more and more in, then they get weaker and weaker so that you end up with a finite vorticity. So the problem with superconductors is that I can't let them get weaker and weaker because they're quantized. So they've all got vorticity plus or minus 1. But that's actually not such a big problem. All you have to do is rescale all your variables because the magnetic field is then going to get big. So I put a d squared in front of this definition of vorticity, so vorticity says finite up here. In order to get a sensible equation for magnetic field, I have to rescale magnetic field with 1 over d squared, where d is the sort of typical separation of vortices. And what that means is that if I've got a lot of vortices and they've all got magnitude 1, then I'm going to get a large magnetic field in the limit. So these are the equations that you have with the delta functions in. And so it's easy to convince yourself that you do this limiting process, and what happens is these delta functions turn into a vorticity. And so I have still the London equation, but now instead of a sum of delta functions on the right-hand side, I have this this vorticity, this smooth function. So this is sort of, as I say, the opposite of the point vortex method. If you were trying to numerically solve this equation, you might replace this by a sum of delta functions. I'm sort of starting off with a sum of delta functions and saying I want to smooth this out and replace it by a continuous vorticity. Okay, so when you do it the other way around, you sort of start off with the Euler Equations. I'm sort of missing an equation now. So let me just go back. So this is all that I had before, plus this law of motion. And now I've got this extra omega, so I've now got one equation, but I've got two unknowns. So I don't have enough equations anymore. And what I'm missing is a statement about vortex conservation. So while I was tracking individual vortices, I'm never going to lose any. They're all going to, if I start off with 10, I'm always going to have 10, unless one goes through the boundary. But, if I'm on an infinite domain, the number of vortices is not going to change. But as soon as I go to this continuum limit, I don't have that anymore. And so the equation that I have to add in is an equation for conservation of vorticity, that I have to, by hand, add in this extra equation. And the way to derive that equation is to suppose that, suppose I choose a curve, a closed curve, which borders a patch of material. So I suppose S is a little patch of material. And suppose I have the velocity field, which is convecting all these vortices. So it's the velocity field of the vortices. And now let this patch of material also be convected with the same velocity field. So if that's true, then no vortices can ever enter or leave that patch of material. They can't cross the curve, can't cross the boundary. And so that gives me the conservation law that says that the convective derivative of the integral over this patch of the sum of delta functions is equal to 0. Because this integral just counts up how many vortices are inside this patch S. So the number of vortices doesn't change. That means the convective derivative of this guy doesn't change. And now this is in a form where you can do this homogenization limit, where this sum of delta functions ends up becoming the vorticity. So my conservation law is the convective derivative of the integral over the surface S of omega is equal to 0. And then if I use Reynolds' transport theorem, I can take this convective derivative inside the integral, and it becomes the usual time derivative plus the divergence of v omega. So this is an integral form of my conservation law. But because the patch of material S was arbitrary, if this holds for all surfaces, for all patches S, then I've got an equivalent differential form. It says that the integrand itself has got to be 0. And so my law of conservation of vorticity is what you would expect. It's just that the standard conservation equation for anything advected with velocity v, if it's conserved, then omega t plus divergence of omega v must be equal to 0. So I show you this because tomorrow we'll do the same thing for filaments, and it's a little bit less familiar when you do it for filaments. So I'm hoping that this was sort of obvious, and it's a little bit less obvious in the case of filaments. Okay, so I'm almost there. I've just got to tell you what is this velocity field. So we've got the London equation with a vorticity on the right-hand side. We've got conservation of vorticity, assuming that I had this velocity field v, which was advecting all the vortices around. Now I've got to give you what is the velocity field v. And this is where, so exactly like this morning, I'm going to appeal to mean field theory and say that, we saw that I had to rescale magnetic field with 1 over d squared. And that says that that's the size of the magnetic field. So the gradient of the field is due to every vortex is sort of 1 over d squared. And then there'll be local perturbations due to the neighboring vortices. But we saw that even when they get close, the gradient of the field due to your nearest neighbor is 1 over the distance of that neighbor from you. So that's of size 1 over d, if d is a typical separation. So your nearest neighbor interactions are 1 over d, and your mean field is 1 over d squared, so the mean field is going to dominate in the limit that d goes to 0. And what that says is that the law of motion is simply v is equal to minus the gradient of h, the h that you get when you've averaged over all these vortices. And note that in this case now, this gradient is not singular anymore because you're not noticing individual vortices anymore because I've smeared them out into a vortex density. So the final model that you get is this guy here. So I've got the Landau equation minus Laplacian of h plus h is equal to omega. I've got a law of motion that says v is minus grad h. So if I combine that with my conservation of vorticity equation, I get omega t minus the divergence of omega grad h is equal to 0, and then I have my usual boundary condition. I've been, when I wrote down all these sums of delta functions, I didn't have any ni's in there. I didn't allow for plus or minus 1. So I've sort of been assuming that all the vortices are positive. You can do the same thing if you have mixtures of plus or minuses in the same neighborhood, it's not so clear, and what you'd actually expect is that they would all attract each other and annihilate very quickly. But if you have a patch of pluses over here and a patch of minuses over here, then you can imagine doing the same thing. And so if you did this with negative vortices, what you would do is have to change the sign on the law of motion, remember? And so what happens when you allow vorticity to be either sign is that this omega here becomes a mod omega, so that the pluses move one way and the minuses move the other way. So if you're going to allow negative vorticity, you have to put a modulus sign in here. Okay, so let me show you how those equations that we've derived through this averaging procedure relate to the Euler equations that we've been learning about in the morning. And it's so because we sort of haven't seen this conservation law directly, I just wanted to show you how this is the same as the Euler equations. So if you do the same thing in my notation with fluids, then this minus Laplacian of psi is the sum of delta functions. You just replace that by an omega on the right-hand side. And the mean field approximation would tell you that the velocity of an individual vortex becomes the velocity with which they're convected is just the gradient, the perpendicular gradient of psi. So this is what you would get if you did the same limiting procedure on here, and then you would add in this equation for vortex conservation. So this is the Euler equations. It's written in this sort of stream function vorticity formulation of the two-dimensional Euler equations. And even when you write it as stream function vorticity, you don't often see it written like this. Normally, you see it written with this Jacobian term. So just to show you, so if U is the curl of 0, 0 psi, so the divergence of, so let me just show you again. So this divergence of omega v term here, and v is the perpendicular gradient of psi, so that's omega times the curl of 0, 0 psi. So that divergence of omega curl psi, if I expand that out, that's grad omega dot curl psi, which is grad omega dot the perpendicular gradient of psi, which is this combination of derivatives, which is this Jacobian. So usually you see this equation written in this form. But it is equivalent exactly to the procedure that I've looked at. And it's sort of interesting to me that you can derive the Euler equations like this, because you sort of imagine the Euler equations are from Newton's laws, right? That it's conservation of the force is mass times acceleration. But in fact, you get the Euler equations if you just say there are these things called point vortices, and they're convected with the fluid, and they generate fluid. And then vortices are conserved, and you get the same thing. It's sort of, normally you do it the other way around. You derive them through Newton's laws, and then you prove conservation of vorticity. But you can actually do it backwards. Okay, this is my last transparency. I stressed earlier that there was, even though you had this analogy, there's only one term, well, two things that are different in the equations. There's an extra term in the Landau equation by comparison to the vorticity is Laplacian of stream function. And then you've got this rotation of the velocity that it's along the line of centers instead of perpendicular to the line of centers. But this extra term, giving you a length scale, is quite important because what it means is everything I've done so far has been on the length scale of the penetration depth. So if I've got a finite sample, I'm assuming my sample is the size of the penetration depth. And penetration depth in physical superconductor is about 1/10 of a micron, maybe a micron if you're lucky. And so if you've really got a finite sample on that size, you're dealing with small devices. And if you've got something which is a bit bigger, then maybe you want to write down the equations and you scale back onto the sample size instead of using the penetration depth as your length scale. And if you do that, then that introduces another parameter in the equations, which is the ratio of those two scales. So you've got, I was sort of assuming I had only one length scale, which was the penetration depth, but now I've got another length scale, which is the size of the sample. So you get this ratio of those two lengths, which appears in front of the Laplacian term here. And so if lambda is of the order of a micron, and suppose L was even a millimeter, still pretty small sample, but that means this epsilon is 10 to the minus 3. So epsilon squared is 10 to the minus 6 then. So you might imagine, well, I should take the limit in which epsilon goes to 0. So you have to do that a little bit carefully because it multiplies the highest derivative, so you can get boundary layers and things like that. But apart from boundary layers, if you just cross this term out, then this equation just tells you that H is equal to omega, which is actually not so surprising. So we've seen that the magnetic field in a superconductor penetrates by means of vortices. It's carried by these flux tubes. And now these vortices have been smeared out into a vortex density, so it's not so surprising that the magnetic field should be equal to the vortex density. It's sort of just saying that the vortices are what are carrying the magnetic field inside the superconductor. So if you put H is equal to omega and then you substitute it into this conservation equation, what you end up with is this nonlinear degenerate diffusion equation. So you have an HT as divergence of mod H grad H. And so the reason that you're getting diffusion is because of the rotation of the velocity. So these two extra effects are both coming in here. One, that I've got this length scale, and two, that I've got this rotation of the velocity. And it's the fact that like vortices want to repel each other is what's giving you the diffusion, that everything wants to spread out. But it's degenerate diffusion. The diffusion coefficient goes to 0 as the magnetic field goes to 0. And so this is well, if H was positive, this is a well-known equation. It's known as the porous medium equation. This is a slightly interesting version of it because normally the porous medium equation is for the pressure, and it should be positive. So you only have this equation for H positive. Here you're allowed to have H negative, and you get around that by putting a modulus sign in the diffusion coefficient. So this, when you get to this stage, you see that the fluids and superconducting vortices really behaving very differently because of this rotation of the law of motion. Okay, so that's the end of today's lecture. Tomorrow we'll look at vortex filaments, and we'll basically do a similar sort of thing. We'll see how vortex filaments are described as delta functions in the London equation, how they move about, and then how you might homogenize them in order to get a three-dimensional version of the Euler equations. Okay, thank you for your attention.